Alrighty, welcome back. So last week we talked about simulating data from statistical distributions. And this was useful for things like illustrating mathematical and statistical concepts. For example, on the lab, we illustrated how the central limit theorem works. But really when we talk about doing statistics, we don't really mean some of that theoretical mathematical stuff. What's probably relevant to an R user and a data scientist like yourself is to work with real data. And so what we are often trying to do is make some claims about what's going on in the real world based on the sample that we observe in our data. So let's give an example. First of all, in the code in this lesson, you're going to want to use two new libraries two new packages that we haven't used before. These are modelR and infer. And we're also going to use the built-in data set, which is called diamonds. So if you want to follow along, go ahead and load those things up, and we'll use the tidyverse as always. So consider this diamonds data set. This data set contains information of about 50,000 diamonds that are sold in shops for rings and so forth. And we're just going to focus on the premium diamonds, the absolute best quality ones for now. And so let's suppose that we're looking at this variable called table. And that variable refers to the size of the flat surface on top of the diamond, I guess the part that's sparkly if you're showing your bling. And so we want to know what the mean table size of a premium diamond is. Now we can look at our data. We can say, well, in this data set, there's about 14,000 premium diamonds. And among those diamonds that we have observations for, the mean table size is about 58.7, I believe this is millimeters. But of course, this data set does not contain every single premium diamond that ever existed or ever could have existed in the world, right? This is a sample. It's a large sample, 14,000, that's pretty good. But this is just 14,000 specific diamonds out of all the infinite diamonds in the entire universe. And so the true mean of premium diamonds, the true deep spiritual average of these types of diamonds, is not probably exactly 58.741. If we knew the actual statistical distribution that generates in the universe premium diamond table sizes, it would probably not have a mean of 58.741. So what we want to ask ourselves is, how would I find a reasonable range of guesses? I can't really know exactly what the true mean is, but I have this data, I have this sample, and I would like to use it to come up with some reasonable guesses about approximately what the true mean probably is. And so hopefully you have some idea of how we might go about this. We said that the mean was 58.7. We could also look at how much it varies. We could look at the spread and say the standard deviation of these table sizes is about 1.48. Now I'm going to stop right here and say that this class does have as a prerequisite some beginner statistical information. So if what I'm saying now sounds completely new, if the word confidence intervals doesn't ring a bell here, I would suggest that you pause the video and you do some of the optional reading on confidence intervals and catch up to speed there. Because I'm not going to cover all the details of calculating confidence intervals. I'm going to assume you've seen something like this before. But let's talk about it a little bit. So hopefully you remember that the way that we typically create confidence intervals for a mean is using the t-distribution. And so here I'm using this function t_test, which comes from that infer package. Technically this runs a t-test. We'll talk about hypothesis tests next week, but it also simultaneously will calculate the confidence interval for you. And so here I'm just going to look at the upper and lower bounds of that confidence interval. And here we have a conclusion that a reasonable range of guesses for the true mean of the table is something like 58.7 to 58.8. If I showed you a few more decimal places, it nuances it a bit further, but roughly speaking, we have this range of kind of 0.1 that we think captures probably the true mean of the population. And so what we would say, the phraseology is, based on this sample of about 14,000 diamonds, we've decided that we're 95% confident that the true mean is between 58.721 and 58.771. So what do we mean by this confidence? That's kind of a very specific word that's used in statistics. Well, here's how I picture it, or many people picture it, I suppose. You have some distribution from which these values are being drawn. Maybe it looks like a bell curve. And there's some true mean of that distribution. And we don't get to know about this, right? The universe generates diamonds, and those diamonds have some table size, and we only get to observe the ones in our sample. And so if we use our sample to make a confidence interval, we hope that it captures the true mean, but of course we can't know for sure. All we get to see are these blue lines, the bottom and top end of our confidence interval. And if we were to somehow take, say, 20 samples and make a separate confidence interval for each one, if that's a 95% confidence interval, that means we expect 95% of those intervals to successfully capture the true mean. So here we have 1 out of the 20, 5%, that happened to miss. We just happened to get a sample that had kind of a higher sample mean that moved our confidence interval boundaries up, and alas, this was not correct. We did not have the true mean in the interval. And you might say, well, how do we know? And the answer is, we don't. In real life, we just get one sample, we calculate one confidence interval, we cross our fingers and hope that sample didn't mislead us, and that indeed we captured the true mean. But maybe we didn't. So having said that, we've got our confidence interval, and let's ask ourselves, what assumptions went into that calculation I just did? I just shoved some data into a function called t_test. You have to be careful when you're learning statistical computing, because it's very tempting to use all these nice functions that are out there and all these convenient outputs that just give you p-values or intervals, and not to really understand the assumptions required to make that process valid. So what assumptions did we rely on here? Well, one thing we relied on was we used the t-distribution. So I want to dig into this a little bit. Hopefully you remember from last week, I asked you to understand that the t-distribution is kind of a bell shape, and you can really interpret it the same as the normal. You can use those two interchangeably as far as we're concerned. So the t-distribution has this bell shape, and we might be tempted to look at our data and say, well, does our data have a bell shape? And in this case, when we're looking at this table variable, it roughly does, or at least there's not some kind of compelling reason to be concerned, right? The pink bars here is the histogram of our data, the blue is an overlaid normal distribution. They fit okay. And so you might say, great, we have a bell curve, and I remember from my intro stat class that when I have a bell curve, what I often want to do is I want to look at the 95% area under that curve. I want to ignore the bottom 2.5% of extreme values, ignore the top 2.5%, and just get the values between those two percentages. So I want to get the values between the 2.5 and the 97.5. They're called quantiles, but the cutoffs of that distribution. So here what I've done is I've pulled out all those observed values that we saw in those 14,000 diamonds. And I've said, give me the middle 95%. And here I see 55 to 62. Let me remind you of what we got when we used the t_test function. We got this very narrow window, 58.7 to 58.8. Those are really different, right? This range here is much larger than this range. So something went wrong here. Well, not wrong, but something went different in these two steps. Let me show you what happened. So here's our data. Here's the histogram of all those values for the table variable that we observed. And these blue lines here are the 95% cutoffs. We are saying that 95% of the observations fell between these two values. And you can kind of see that in the plot, right? Maybe 2.5% is this pink area over here, 2.5% is the pink area on the bottom here. But this isn't a statement about the mean. This is not a statement about where the center of this plot lies. This is a statement about where all of the values tend to fall. And so you might say to yourself, well, we have an awful lot of information here, right? We have 14,000 diamonds to work with. We're probably pretty sure about where that center is. I would be super surprised to find out that the true center of the real distribution of the universe of diamonds was right here, was at, say, 56. And that somehow, in this particular sample, we got so unlucky that our 14,000 values kind of looked like their center was closer to maybe 58. That would be weird. So let's illustrate this with a subsample of the data. We have those 14,000 values, right? What if we only had 100? So here I'm going to subsample down to 100. And now I'm going to say, where does the middle 95% of those 100 values live? And lo and behold, we actually got the exact same range. The middle 95% of the 14,000 values was 55 to 62. The middle 95% of the subsampled values was also, it turns out, 55 to 62. Now these two distributions are not totally identical, right? This one comes from 100 values rather than all 14,000. You might notice the little tail is missing there. But the distribution of the data is approximately the same. So if we're getting the same answer from 100 values and 14,000 values, that should tell you that that's not really the question we're trying to ask. The question is not, where does 95% of my observations fall? The question is, what is a range such that I am very, very sure that the center is somewhere in that range? So here's back to our original data, and here are the boundaries for the confidence interval we calculated using that t_test function, the confidence interval for the mean. And you're like, well, that's just one line, and it looks like it's one line right at the mean. That's because our confidence interval is so narrow. So let's do like a CSI zoom and enhance. Bam. We are super sure about where the mean lives. We aren't sure about where that next diamond might fall. If I say, give me a diamond and I'll measure the table of it, I don't know that it's going to fall in this tiny, tiny window. It could really fall kind of anywhere in this distribution. But if I say to you, what is the true mean, the true average of every diamond that ever lived, I can feel pretty good about my guess, about guessing that it's somewhere around 58.7. So I really want you to be careful here with the distinction between many observations versus the sample mean of those observations. And in particular, something that we used, something that we learned about last week, was my favorite thing, the central limit theorem. And the central limit theorem applies to the sample mean. Regardless of how your data looks, in this past example, our data looked kind of like a bell curve. But we don't care. It's the sample mean we're interested in, and because of that central limit theorem, we know that the sample mean comes from a distribution with a bell curve shape. And that's why when we did that t_test function, or any similar function you choose to use, we end up with this very specific, narrow range of guesses for the true mean.